In this video, we're going to discuss the basics of probability theory by looking at several formulas that are important, the most important formulas, and we are going to then apply some of these formulas to situations that would arise or will arise in physical chemistry problems, such as the probability of finding a particle in a certain location and other problems that are related to physical chemistry. But before we can get to the physical chemistry type problems, we first need to learn the basics of probability. So let's start with first a definition of what is probability. So first we know that the probability of an event, which we'll designate as P sub j, occurring is that a number between 0 and 1, identified by this inequality set. So for example, if we have a standard deck of 52 cards with 26 black cards and 26 red cards, the probability of drawing a red card from a standard deck of 52 cards is 1/2, or would be 1/2. The probability of drawing a black or a red card from a standard deck of 52 cards would be 1, and the probability of drawing a green card, that is, where the colors of the on the card are what's imprinted on the card is green, from a standard deck of 52 cards would be 0. So another way of saying is, if that event will definitely occur, the probability is 1. So picking a black or a red card would definitely occur, that would be 1. If the event will definitely not occur, the probability is 0. So you won't pick a green card out of a standard deck of 52 cards. And in between, and exactly halfway in between in this case, picking a black card probability out of a standard deck of 50 cards would be 1/2. So continuing with basic definitions, the mean of an event Pj occurring would be the sum between I equals 1 and n of the product xi, that's the event itself, and the probability of that event. So let's take a very familiar example on the next blackboard. Let's suppose that you had 4 exams, and that on exam 1 you made an 80, on exam 2 you made a 90, on exam 3 you made a 90, and on exam 4 you made a 100. Well, the probability of each exam is exactly the portion of the probability of 1, the total probability 1, and each exam has a 1/4 probability. And so if we calculate the mean using the formula, it would be, 80 times 1/4 plus 90 times 1/4. But if we put that in a form that's more familiar, which is just taking the average or the weighted average, we would just do what? Add up the scores of your 4 exams and divide by 4, and we would get the mean, or average in this case, of a 90. So mean and average in a lot of cases mean the same thing. Or in simple cases, it could be slightly different in more sophisticated examples. So let's start looking at some probability formulas that are used to calculate probabilities of commonly occurring type events. This is called the binomial distribution. P sub m equals n factorial over m factorial n minus m parentheses factorial times P sub m q to the n minus m. So how would this be used? If we look at example 21-2, where we are doing a coin toss 10 times, so we're doing 10 tosses of a coin and that gives us that n equals 10, the n in the numerator. We want to get exactly 5 heads, and so heads is the event that we're trying to get, p sub m, so the m is 5. The probability that we get heads is 1/2, right? 1/2 of the time we'll get heads. The probability that we do not get heads, or that we get tails, is this q, and that is also 1/2. So that's so we've defined all of the value, or the parts of the formula, right? N is 10, m is 5, p is 1/2, and q, not heads, is 1/2. So p sub m, or probability of getting exactly 5 heads, would be 10 factorial over 5 factorial 10 minus 5 factorial times 1/2 to the 5th power and 1/2 to the 5th power. If we write that in a more in a form where it's easier to simplify, let's write 10 factorial as 10 times 9 times 8 times 7 times 6, and then it's times 5, 4, 3, 2, 1, but let's write that as 5 factorial. And then in the denominator we've got 2 5 factorials. Let's write one of them like that, and the other one like this. And we've got 1/2 to the 5th times 1/2 to the 5th, which gives us 1/2 to the 10th. And then we can do some cancellation, right? A fair amount of cancellation. 2 5 factorials cancel. The 5 times 2 cancels out the 10, and the 4 goes into the 8 twice, and the 3 goes into the 9 3 times. And if we continue, that gives us 36 times 7 times 1/2 to the 10th, which is about 0.009765, and if we combine all that together, we get approximately 0.246. So what does that number 0.246 mean? If we toss a coin 10 times and we want to know the probability of getting exactly 5 heads, it's going to happen roughly 1/4 of the time that we'll get exactly 5 heads. We could actually handle a probability problem like that, a coin toss, by drawing a chart, but it gets very complicated when we have so many tosses. I'll do it for, say, 3 tosses to show you how we could do another probability problem. So let's say, let's show it. So we get heads, tails on the first toss. If we got heads the first time, we could get heads the second time, or we could get tails the second time. If we got tails the first time, we could get tails and heads, and tails and tails, and we toss a third time, heads, heads, heads. So a similar problem to the one that we just did that we're able to see in chart form is so let's say we tossed the coin 4 times, and we want to know the probability of getting exactly 2 heads. So we see that could have occurred here, 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 or here, and that is 1, 2, 3, 4, 5, 6 times out of how many times? Or about 30, or actually exactly 37.5% of the time. But this is the formula that we would use if we have any complexity to the event whose probability we're trying to determine. So for other types of situations, we need what is called a multinomial formula. So with the binomial distribution, we have, it's called binomial because by 2, there are 2 events used in that situation, or two events that it can occurring at the same time that it can be used to describe In the previous example, that was either heads or tails, but what if there are more than two events? Then we use the multinomial distribution. So let's see how that is used. Let's suppose that we have a deck of 52 cards, and we want to deal the entire deck out into four 13 card hands, and we want to know what the probability is of that occurring. So the n factorial would be 52 factorial, and the n1, n2 to nn would be the 13 card hands, but there are four 13 card hands, so that would be dividing by 13 factorial 4 times. This is a huge number, 5.36 times 10 to the 23rd, or bigger than Avogadro's number, so we're not going to run out of unique bridge hands. So there's another problem, or you'll be doing a problem of this type in homework problem number 8. I should note that practice problem for the binomial distribution problem will be a homework problem number 6 that will see that you know how to apply this formula correctly. So let's suppose we have this probability question. Alpha particles are being emitted at 1.5, a rate of 1.5 per second. Calculate the probability of 0, 1, 2, 3, 4, or greater than or equal to 5 alpha particles being emitted in a 2-second interval. So the formula we use for this is called a Poisson distribution formula. It is sort of like some of the other formulas, but it has an exponential term in it where we've never seen that before. This constant A is defined as lambda delta t. In our particular problem, the lambda is the 1.5. and so A is going to be 3. And so let's, on the next blackboard, see how to calculate all these probabilities using this formula. So P sub 0 is going to be A to the 0 divided by 0 factorial e to the minus A. A we calculated on the previous blackboard is 3, so that's 3 to the 0 e to the minus 3. 0 factorial is defined as 1, and of course 3 to the 0 is 1, so this is just e to the minus 3, which is approximately 0.05 to 1 or to the second decimal place. It's that. P sub 1 is going to be 3 to the first over 1 factorial e to the minus 3. And so that is just 3 times e to the minus 3, which is 0.15. P of 2 is going to be 3 squared over 2 factorial times 0.15 e to the minus 3. So that's 9 halves times e to the minus 3, and it's easy to see that that's 0.22. And if we calculate the others, we see that this is also 0.22, and this one is 0.4. So we have all the probabilities we were asked for, except for the last one, we've got P of 0, P of 1, P of 2, P of 3, and P of 4. The P sub 5 is going to be, P of greater than or equal to 5, which would be 5, 6, 7, 8. That would be impossible to calculate because we'd have to keep doing it without an n to the n, but an easier way to do it is say, okay, the probability of any number of alpha particles being emitted is 1, and if we subtract from that the probability that 0, 1, 2, 3, and 4, so if we add all of these up, it turns out that they are approximately 0.81, and therefore the probability greater than or equal to 5 is roughly 0.19. Homework problem 11 that you're going to do is a similar type of problem. So let's look at one more type of probability situation. Actually, these are the most important types of situations for quantum mechanics. So these are called continuous probability distributions, such as would be the case inside of an atom. An electron could appear anywhere, right? And the way we find those probabilities is by integrating the probability at any location x. We also would need to sometimes find the mean, and that would be defined as x, p of x. Remember, an integral is a sum, and the way we initially defined a mean was x, I, p, I, right? So this is really the same thing, right? Because we're multiplying x's times p of x's. The probability distribution function that we work with, the p of x, is very often a Gaussian distribution that looks like this. So here is our Gaussian distribution, probability distribution, and if we were calculating the mean of a Gaussian distribution, it would be this integral. In homework problem 17, we will calculate the mean distribution for the probability of a particle's location. We won't use the Gaussian formula, we'll use another p of x that's defined in that problem. So we've looked at a variety of probability situations, defining probability as being a number between 0 and 1. We've talked about the probability of simple type events, getting heads or tails on a coin toss, picking cards out of a deck of cards, a little bit more complex, and then we've gotten successively more complex in our examples till we come to the most important type of probability problems, probability distribution problems, those that are continuous, because those are used to define things like particles, location in space. We've looked at the Gaussian distribution formula and what the mean would be as an integral formula, and we'll look at that in problem 17 of the homework. So this concludes this video on probability, and we'll follow up with lots of examples, most of them fairly similar to the type that are in this video that you'll be doing in the classroom.